And now we're ready to go with Andres Freund, who is going to talk to us about what went wrong with AIO, which is a huge project in Postgres, which he's been working on along with other people. He's one of the longtime contributors to Postgres that we are very happy to be hearing from today. Thank you. Please welcome Andres Freund.
Cool. Hi. This is a different talk than I've normally given, so this might or might not work. We'll see whether it does. The goal with this talk is that I've been working on AIO for a long time, and if you look at this timeline so far, that might actually look reasonable, except that it's not 2021, it's 2025, and between there and here, there was a lot of time. And it was a very large project, and it's okay from some point of view for that to take long. But I think this took longer than I thought it would, and I think it took longer than we as a project can really afford if we want to address all the architectural issues that I think we do need to address in the next few years, because otherwise we'll just suffocate under our own weight at some point. The other part for choosing to not do the typical bragging about your feature type of talk was that when I was submitting the talk, that I was actually not sure whether AIO would get in. So I thought it would be nice to submit a talk that I can give either way. But I can't quite not brag at all, and it also does explain why I think it's important to address some of these issues. So here's just a small slide showing some before and after of a bigger than memory workload, and it just shows the fractional performance effects of AIO on both a local fast NVMe and a cloud storage that has about 3 milliseconds of latency. And you can see that even though AIO at this point only does a few things, there's some case where it can help a lot. And in all of those cases, we can make that multiplier much bigger over time. So, and just a small thing of the type of example of the type of architectural issues that I think we do need to address. And unfortunately, it's not that you can address one of them and then reap the full benefits. You have to kind of solve one massive architectural challenge and then another one to actually get really benefits. And if each of these type of projects takes us 6+ years to do and several people to do, I think we'll have a problem. So I'm trying to look at, in this talk, at what I spend time on, and perhaps some of the things I know that I could have done better in hindsight, or even at the time, and some others I'll just try to describe the problem. I think one set of issues is that just as a project, we haven't done that many large architectural changes of this size, I think, and we aren't quite set up to do that, I think. And I think I don't really have solutions here for most of it, but for some of it, I think we have already made progress since I started working on AIO. One issue there is really that we have the older the area of the code is, the less tests we have. And unfortunately, most of the architectural issues tend to be old, so it will all typically affect things that are not very well covered by tests, which then makes your iteration speed a lot lower than what you would want it to be. And obviously, if you build on architectural, if you have a system that is built on architectural assumptions that you want to now change, and that architectural assumption has been there for 35 years or something in some cases, there are going to be a lot of dependencies on those architectural assumptions, and that means that you have to really look at the whole system and try to find all the tendrils of what you change, and that just takes a long time. I think also as a product, we tend to not be very good at incrementally merging features or changes. And I think that's to some degree very justified. If you look at some other projects that are much more developed on trunk, that does not necessarily result in stability and has its own set of concerns over the long term. but also it means that you have to do a lot of work at once and then integrate all of that, and that just sometimes is not like humanly really possible. And you have to really work very hard at trying to find like pare down what you work on to like some workable subset. And one issue with that is that the subset of things that you can integrate will often be so small or so boring that it's actually very hard to justify merging it. If it's like some change that like you actually have no user of the change, like nobody outside of the people working on the feature actually sees the benefit of the change because it's so like 5 levels steep a dependency. It's really hard to justify merging it. And I think we have erred a bit too far on the side of being conservative around that. And you probably should experiment a bit more with moving a bit, like allowing a bit more experimental things in, not to the full degree, but a bit more. The project, like how I went about working on AIO was that at first I built a prototype, and I started doing this when Linux introduced the AIO ring AIO backend or API. And the reason for that was that it was the first kernel level AIO API that supported buffered I/O. Traditionally, most of the asynchronous AIO APIs across most operating systems, somewhat surprisingly, only support doing direct I/O, that is I/O that is not buffered by the kernel and the kernel page cache. And for lots of workloads, that's not really feasible to do because you can't know ahead of time like how large shared buffers is, and particularly today, you can't reconfigure shared buffers at runtime, and like it's not suitable for cases where you share the machine with other users because then you can't dynamically change the amount of memory. So, and also when you want to use direct I/O, you actually need to be very good at a lot of things because suddenly your I/O performance is very poor if you don't use AIO, or if your AIO implementation is not yet very good. Whereas if you fall back to buffered I/O, it doesn't matter that much if you don't get like some details quite right. I mean, not correctness-wise, but just like performance optimization-wise. After working on that prototype, Thomas Munro worked on adding worker mode and then Postgres AIO backend to AIO. I had initially thought we might actually go for trying to do a native AIO implementation for all OSs or something. That was probably not a feasible path, so I'm very glad that the worker mode was added, and it works way better than I would have thought possible. Like, you can get really competitive performance, and in some cases it's actually faster than using kernel level AIO because the parallelism, CPU parallelism that you get from workers can speed things up. As I said, Thomas also added a Postgres AIO backend. That is, turns out to not necessarily have been a very good idea. But it was very interesting to see what the design impacts would be of trying to use it. And it turns out that it's not a very good API. And particularly not if you want to actually use only the standardized pieces of the API, because it just does not suit the way we have to do things very well. There really were a lot of, while working on the prototype, there were a lot of things that I did not know how to do ahead of time. And because of that, there were lots of experiments that had to be tried and then discarded and tried a different way. And it was definitely at some point clear that it would have to be a prototype that has to be rewritten from scratch to actually be mergeable, just because like the amount of technical baggage that collected over time was just too large. As part of the prototype, I also tried to find all the different potential AIO users that I think would be important that would have different design implications. It's a very different thing to have to do asynchronous I/O for a sequential scan or a bitmap heap scan or something, or from actually needing to do writes. There's very different constraints on that already, and then if you want to do writes from the buffer pool, that's a very different thing than having to do writes for wall writes, because wall writes typically are done in a critical section where you are not allowed to allocate memory, and you're not allowed to basically occasionally fail or something, because then that will take down your server, because at that point you already modified the in-memory buffers, and you can't just fail to complete the wall insertion. And that turned out to have really massive downstream design implications. And it took me a long time to even get that anywhere remotely right. So the very basic AIO API, and this is not how it looked in the prototype, this is roughly what it looks like today, is that you have to get a handle, and that handle you can then associate with some AIO, and you can register callbacks on that handle that happen on completion and at start of the AIO. And you can do things like update the buffer descriptor to say, hey, now you can unset the IO in progress flag now that the IO have completed. And once you've done that, the IO may be executing, and you can do other things like start another IO, do some CPU intensive thing or whatever, and then you can wait for it. And I mostly have that here because it will actually is kind of required. That split of like having to get the handle and then doing IO on that, like associating AIO with that, is important to understand for some issues in a second. So one thing that I ended up spending a tremendous amount of time between sometime in 2021 and basically 2024 on is that the prototype worked very well in some cases. Like if you did direct IO reads on a sequential scan, you would beat like buffered sequential scans like very, very easily. But if you had cases where like you had used buffered IO and the data fit in the kernel page cache, it actually was surprisingly hard to beat the current model, at least initially. And part of that was that the locking overhead in the prototype was just too high, and that was, I'll go into reasons why that was in a second. And then one part of the prototype that I spent by far the most time on was trying to do concurrent wall writes. Currently, Postgres only has one wall write in progress at a time. And if you think about like how long it takes to do an fsync, it actually is pretty obvious why you would want to do multiple writes at the same time. You can, if you do it in the situation where it works, you can get like 4x, 10x in some cases, the write throughput, and that's obviously very cool. But it just turns out to be extremely hard to tune, particularly if you want to deal with different hardware and not having like dozens of parameters to tune it. Like I think in the prototype, I ended up like having like 8 different parameters to control like how to do wall flushing, and that doesn't seem feasible. And like I did not know how to tune it, and if I can't tune it, like how is anybody, like a normal user, supposed to tune it? And it really like wasn't even that you could say like on an SSD tune it this way, because one SSD manufacturer, the performance characteristics are so completely different than from another one. Like on Samsung SSDs, if you have an IO depth bigger than 1 for wall writes, your performance will be atrociously bad. On other manufacturers, it will be atrociously bad if you have an IO depth of 1. And on some of them, you have to do very large writes. On others, you never, ever should do large writes. And I spent so much time trying to understand all of this, and I probably should not have spent quite that much time. But it also turns out to be extremely workload dependent. Depending on the Postgres workload, when you do batch copy into the database, you have a completely different wall write pattern than if you do concurrent PG bench type things. And particularly concurrent PG bench is actually like extremely hard to tune because each transaction only writes so little wall that you end up with like lots of different things happening and fitting on the same page. So you can't actually do a lot of concurrent wall writes if you don't have a lot of concurrency.
You didn't know this was going to be a problem when you started trying to do wall write tuning. So how could you have predicted that this would go this way?
Yes. I mean, that was my issue. I'm just describing the problem, I think. I think in hindsight, I wish I had not spent half a year in trying to optimize this, because it turns out the optimization actually was not that crucial for the design applications. I thought, like, I was not sure of that, so hindsight is 2020, but I did spend like time trying to find like algorithms for how to tune like the I/O sizes and all that stuff based on the workload, and that is all cool, and we probably need to do some of that, but it was not in the critical path, I think. The critical path was actually trying to get it working and trying to figure out what are the design implications, and that could have happened in way, way, way less time. And I think I just thought it was a very interesting project, and I spent too much time on that because it was interesting, and it's I think, something that we leave so much performance on the table so that it's actually important for Postgres, but it didn't help that I did it like 2 years ago, because it's not like we have optimizations based on that now. There were a few major architecture mistakes that I did not catch very quickly in the prototype. One of them was that initially I was trying to reduce the number of I/O Uring instances. And one thing about I/O Uring is that each I/O Uring instance has its own file descriptor. And if you want to wait for I/O that is initiated by another backend, you have to have access to that I/O Uring instance to be able to wait for it, because the system call for that has a file descriptor argument. And that means that all those I/O Uring instances have to be created in Postmaster. So if you do one I/O Uring instance per backend, you end up with a lot of file descriptors that have to be created and reserved basically at at Postmaster startup. And I was very worried about that, and because of that, worked very hard on making it possible to only have like a fixed number of I/O Uring instances. I think for some reason I chose 8 initially. And it turned out that the design implications of that were extremely severe and very, very hard to address, because you now needed locking when submitting I/O via I/O Uring, which you did not need to do when you had one I/O Uring instance for each backend, because the submission side of doing I/O would be otherwise private. And the cost of actually having a file descriptor, on Linux at least, is basically, I think, 56 bytes or something. Don't quote me on this number, but like it's a few dozens or hundreds of bytes. So it does not actually matter that you have them. But the entire design was focused on not having all those file descriptors open, and because of that, like there were so many downstream design decisions that went wrong. I think that was by far, like probably one of the top 2 architecture issues. And in the version that ended up being merged, we just said like, okay, you have to increase the number of file descriptors that are allowed, and we have one of the I/O instances per backend, and that made it much, much faster and simplified the code a lot. Like the final version of the code that got merged and the prototype, it's like less than a third of the size because of a lot of this. There's also some simplifications that we'll have to eventually do, but like just not having those wrong design decisions really simplified it a lot. And then the other thing that was completely wrong, and where I don't understand how I got that wrong, where like in hindsight it's so obvious, and I think I kind of knew it at some point fairly early on, but I just did not address it, was that initially one could acquire a lot of these I/O handles in each backend. And because of that, the amount of those handles that had to be available in shared memory had to be very large, and it could not be that like each backend had a dedicated number of those handles, because it could be so large that we had to increase that number. And because it was expensive to get those handles, because we now needed locking, because it was dynamically shared between each backend, or each backend could get like ones that were not reserved for itself, the locking for that was expensive, and because of that, like a lot of code was trying to just like pre-allocate and reuse those handles. And the biggest issue with that is that it's fundamentally not correct, because that means that if you have like a query that has 10 cursors open, and each of them does I/O, and each of those cursors does a sequential scan and has pre-allocated 128 I/O handles, and then you do that in all backends, it's not possible to have enough I/O handles for that. And if you want to block waiting for more I/O handles to become free, there's no forward progress guarantee. You can't even have forward progress guarantee on your own backends, because they were in some other parts of the code, and you're waiting for another handle, and that code is never reached, so that those pre-reserved handles were not ever going to be freed. And so there were lots of kind of self-deadlocks or deadlocks between backends where they were waiting for more IOs, but they were blocked on waiting for more IOs on other backends, and it was like, it did not work. And what we ended up with as a design is that you can have exactly one IO handle that does not have IO associated with it, and you can never reuse them from the user space point of view, because that allows you to say, if I need another IO handle, it will just wait for one IO to complete, and then you can get one of the IO handles that's reserved for your backend. And that means that you have a forward progress guarantee, and that made it very easy, because like, it turns out, even if you have, I don't know, I think the current default limit is 64 IO handles for each backend. That's not a whole lot across the number of connections. We use way more space per backend for locks and stuff like that. So that's not, did not turn out to be a big issue. And now we don't need to acquire locks to get the handles, and that made it much faster. That's one of the biggest performance issues with doing, like with buffered IO, where all the data is in the kernel page cache, was the locking required for that. Just because even if it's very small overhead, if you do another atomic operation, even if it's uncontended, for each block, that turns out to be measurable, because it was already CPU bound, so you just add more expensive things, so it will be slower. One other big thing that I did wrong, and where I'm still kind of curious why, and why it was not immediately obvious that that would not be the right thing, is that in the prototype, when I/O was submitted, like there was always the block size of that Postgres uses, so 8K, and then to make those I/Os into larger I/Os, the I/O layer, like the AIO layer in Postgres, like merged those I/Os and then submitted larger I/Os to the kernel. And that means that if you do one large I/O, like if you want to read, like do a sequential scan where you read 128K in a row, you need like 16, if I do math correctly, I/O handles for that, even though that you could do that with one read system call. And when Thomas was working on upstreaming some aspect of the I/O work, he made the decision to use scatter-gather I/O so that you can read more buffers at once, and that actually addressed a lot of the performance issues with the overhead of having to have I/O handles, because you suddenly only did not need it for each I/O. And it turns out that I forgot the exact numbers, but like somewhere, like as soon as you can do more than 4 blocks for each I/O, the overhead of managing the I/O handles basically becomes unmeasurable, even for cases where all the data is in the page cache. Another thing that turned out to be very informative but also very wrong was that the prototype had a new layer that managed getting new buffers for victim buffer replacement. So if you insert more data into a table, or if you read a block that's not currently in the page cache, you have to get a victim buffer. But if that victim buffer currently has dirty data in it, you have to first write that out. That works reasonably well today if it used with buffered I/O, because then the kernel actually can hide all that latency of writing out the data. There's a lot of other issues, like you can get these latency bubbles, because suddenly the kernel decides at some point to write out like hundreds of megabytes of data, and suddenly your transactions get very slow and stuff like that. But it kind of worked. But if you use direct I/O, each of those writes suddenly will be slow, because you're synchronously writing out 8K, and it actually has to go to storage and back. So what I was trying to do was to have some layer in the backend that always reserved a number of buffers that could be replaced. And the worst part was that I somehow integrated it somewhere below buff manager, so that within a read buffer you would get to a code that would write out buffers asynchronously ahead of where you were, and like then sometimes the completion callbacks for that, which were at the time allowed to do their own I/O, would then read. So you could end up in a case where you would read buffers would call write buffers would call read buffers, and that obviously did not work very well. And another mistake, I think, was that we tried to integrate that PostgreSQL AIO backend, and that turned out to just never be stable. the performance is awful on some platforms, like particularly on macOS. It's just atrociously slow. Like, I do not understand what's happening there, but it's just way slower than anything else. And you can only do like 4 IOs by default on concurrently. And because of the way because it does not really allow you to wait for completion of IO in another backend, we had to do really nasty things in signal handlers. On Linux, PostgreSQL AIO was implemented by glibc via threads, so you suddenly had a lot of threads in each backend. It just was a nightmare and had like all kinds of stability issues, and it made really like the tests like fail in random ways that were a nightmare to debug, and partially because we did not have enough debugging infrastructure, but partially also just because I'm pretty sure there's several kernel bugs around PostgreSQL AIO in both in macOS and some in glibc. And I spent a lot of time trying to get that. Yeah, sorry. So to summarize, I think the prototype was absolutely crucial. The experimentation over time made the code quality in the prototype really hard to work with, and it really was slowing down, and I should have probably paid more attention to that. And the biggest one, I think, is that its prototype doesn't have to have production quality performance. And that's probably like where I lost at least a year, and where I would do things differently in hindsight. And also, I did know that like some of that, the way the IO handles were managed were wrong, but I did not address them because it was a prototype, and then try to do workarounds for all those issues.
Did you think it was a prototype at the time, or did you think this was going to be the final product?
I was pretty sure that it could not be the code. Like there was just too many embedded things that were not quite right, and it seemed easier to. I was open to the alternative that it would not need to be. I mean, like I had hope, but I did not believe, to put it that way. Yeah, and like addressing some of the architectural issues earlier would have really, really saved a lot of time. Even though I thought like I would not have to because it was just a prototype and I would do that in the real version. That was like a rather bad mistake that cost I think, about a year. So some of the things that I think worked reasonably well was that we did manage to upstream some parts fairly early on. I think the biggest for that was to do bulk relation extension, and that might sound rather random, but to do bulk relation extension, a lot of fairly fundamental buffer manager assumptions had to be changed. Before that, we never wrote more than one buffer or read more than one buffer at a time. So doing bulk relation extension, that is like extending the relation like by multiple blocks at once, we needed to have the buffer locking infrastructure to do that. We needed to have the error handling infrastructure to do that. We needed to do the buffer mapping table suddenly needed to be modified in a very different way than it was before. And I was surprised how well it worked out to do that as part of bulk relation extension, and that like about more than half of the buff manager related changes that had to happen for AIO turned out to be like partially done somewhere around the bulk relation extension, or motivated and were showing benefits as part of the bulk relation extension. There's some random things like we had to make the memory allocator support allocating buffers in an aligned way, because if you want to use direct IO, they need to be aligned to some sizes. It did not fit on here, but we also had like was it Postgres 16 where we have like a way to enable IO direct IO, even though the performance was catastrophically bad. It was there to be able to add all the infrastructure necessary to do direct IO, and I think that worked reasonably well. And we also found problems that we would have found earlier that way. Like one issue that Postgres has that is that it modifies buffers while IO is ongoing, and it turns out that Btrfs really does not like and suddenly considers the file system to be corrupted because the checksums that it computed while the IO was going on is not correct anymore. And that was actually a good thing to know ahead of time, because that's something we really ought to fix, I think, independent of AIO, because it's surprising that it only causes problems, that the only case we know that it causes problems that are there, and it turns out that Linux actually has a bunch of workarounds for various file systems because of Postgres. because they found that we caused block level checksum failures. And because of that, it has a weird feature where the kernel, while doing the I/O, copies the page in some cases. And everyone hates that part. I did not know that ahead of time that this was partially about Postgres. Yeah. Then one very big thing was a combined set of things was to add like scatter, gather, read, and writes like in a general infrastructure, and then use that in the buffer manager as part of the read stream work. And read streams are basically an abstraction that allows you to do read ahead in cases where you can predict what the next block, what future blocks are going to be that you need. And then they manage like how many IOs you have in flight at the same time and stuff like that. And we were able to, or Thomas was able to get that to be beneficial even without AIO. And then when AIO was merged, it needed, I don't know, 20 lines of changes or something to actually be able to do AIO. And that converted allowed like to introduce AIO users in a way before we had all the AIO infrastructure in, which is good because otherwise if you add AIO infrastructure, that won't actually be tested or used if you don't have users, and there was a fair amount of work to get the read stream to actually work. So that was a very good, I think that was a very fortunate part of how it worked out, and I think I'm really proud of that worked out. And we, like several other people, then started introducing read stream users in parallel with AIO development. One thing where I'm really unsure whether it was all the right call was that as part of AIO, I ended up like being very concerned about being able to test AIO. And part of that was that at the time, we had only the build farm for automated testing of Postgres, but the build farm is only usable for post-commit tests. But for a project of the complexity of AIO, there's no way we could have actually just do post-commit automated testing across platforms. And I find it extremely exhausting to run like 30 different systems, like different Linux distributions, different kernel versions, and stuff like that on a regular basis. So it was really crucial, I think, that we added CI as a sub-project or before actually doing very much towards merging AIO. And I think that worked out really well. I could have spent a bit less time on it, maybe, I don't know. It was, I think we should have done that much earlier, and I think hopefully we'll make other big projects a lot easier in the future. And there's much more we can do around that. A kind of dependency that I ended up doing before finishing AIO was that I worked on the Meson build system, and that actually started when I was working on AIO and was so frustrated with not being able to actually see all the test results on Windows particularly, because at the time we did not have a way to actually run all tests on Windows. You could manually start each of them, but like constantly you would need to maintain that list separately from everything else. And then you would, those tests would only run serially, so the test would actually take like an hour or something, and you would run even out of CI time and whatever. So that was partially being one motivation for working on Meson, and I was, while doing AIO development, just occasionally hacking on it so I could actually have a shorter cycle time. But in the end, it was a huge project that I don't know whether that was really the right thing to do at the time. But I don't know what the alternative timeline would have been. But yeah, that cost a lot of time and a lot of distractions. There turned out to be a number of things that made it easier actually to merge AIO at the end, because mostly I think Heikki did a lot of refactorings for reasons that were independent of AIO, but that turned out to actually make it a lot easier to do AIO. Like in the initial worker logic that Thomas had submitted, it needed to do weird things with like different subsystems, because we now had like suddenly multiple aux processes for one aux process type, and there was no way, it really screwed with different subsystems, because we had like different identifier types for each backend. So there was the proc number, then there was the something in the backend status array, and like each of those needed to be modified separately. And after all of that was unified by Heikki, it turned out like the patch to add worker support like really shrunk that like by half, which is like kind of surprising. and it got easier to start Postgres, postmaster children and stuff like that. So I hope that will also make other projects easier in the future. Another reason that things took long is that life sucks sometimes. I had like several bouts with illness, and physical illness, and parents getting sick and stuff like that, and that just makes it really hard to focus on really large, complicated projects and keep it all in your head. And I debated with myself whether to name that here, but it feels like we should acknowledge that there's other things in Postgres. I also found it really hard to balance doing AIO work and also just doing other committer work. I did end up spending a lot of time trying to get shared memory statistics mergeable, because it had been a patch that had been around for a long time and felt really not nice for it never to progress. So I tried to get it into a mergeable state, and it turned out to be a much bigger project than I had planned. And that was a very large distraction. There's also stuff like security fixes and just other things that is very hard to do at the same time as you developing a major feature. And I don't know what to do about that. The way we are currently set up, a committer has a lot of different responsibilities, and that means that you can't focus fully on developing a new feature. And yeah, it is how it is. And just maintaining motivation is really hard for a project of this size. There were definitely phases where it felt really like a slog that would never end, and I didn't know what to do about that other than make projects not take that long. But yeah. One thing that I wish could have worked out better was to parallelize more of the development. A lot of the time, either I was blocked by other people or other people were blocked by me, but not enough happened at the same time. And part of that was that if somebody else, if I was quote unquote delegating work or handing off some work to others, I suddenly was blocked by that work, and the other people were doing their own thing and had their own timelines, and that at the same time other people were constantly blocked by me, and it didn't really seem very worthwhile to focus on introducing a lot of AIO users before the core AIO infrastructure looked right, because it turned out that had to evolve a lot during AIO development, so they would have constantly needed updating. But it was a really challenging part of making this go faster. So a quick summary of where we are now in 18. The core AIO infrastructure is merged, and there are different backends, or how we call them methods. I don't actually know how we ended up with method, but I think we wanted to not call it backend because of overloading that term even more. So we ended up with methods. Sync is one I/O method that basically just does not use AIO. It still goes through some of the AIO machinery, so that the code that issues AIO doesn't have to have two parallel paths, but it just executes the AIO synchronously and tries to have basically a similar an I/O pattern as possible to Postgres 17. It won't have the same pattern as Postgres 15 or something, because Postgres modern streaming I/O-ified Postgres has a very different I/O pattern than before. So, but it does allow to basically opt out of AIO, and that's, I think, was a very important thing to have, just to be able to de-risk a change of the size. And it could be that we will have to default AIO to that method in beta 2 or something if you find out that it has too many problems. And I don't know what the right answer there is. I think it's good that it's enabled with Worker by default for beta 1, so they actually get some some experiences out there, but we'll have to see what we do there. It also has an IO Uring method, and one of the somewhat challenging things is that there's lots of cases where IO Uring is a lot faster, that it's typically, if there's lots of random IO, it's a lot faster than worker mode, because the dispatch overhead to a worker is just noticeable. But for sequential scans that read a lot of the data, it turns actually out that doing I/O with workers is sometimes faster, because they can parallelize things like checksum computation or just memcopy from the kernel page cache. And the kernel page, that memcopy actually turns out to be a bottleneck in some cases. So doing that in workers makes things faster than actually doing that asynchronously in the kernel. There are a number of things that use AIO now that is as the read stream interface via the read stream interface, and in 17 that was mainly sequential scans and PG prewarm, and like I think there was maybe one more small user, but I don't remember. And then in 18 we have bitmap heap scans, vacuum, and a lot of other like extensions. I don't know that I think. Stat tuple and stuff like that. Auto prewarm now can use like the read stream interface and like a lot of other smaller kind of things, but bitmap heap scans and vacuum are the biggest new ones. There's no write support in 18. That's not quite right. The actual core AIO subsystem can do writes, but like on the MD.C, like the SMGR abstraction and buffer manager, on those levels we actually need to do a bit of work to actually make writes safe. And yeah, but I think it shows good performance results on a number of cases, and it won't do anything for others. And there might be some regressions. We hope that you all test it for beta 1, and hopefully they won't be too bad. Infrastructure-wise, the next things I think to do are to make the buffer manager ready to do writes via AIO. That's mainly needing to be like coordinate buffer locking and waiting for I/O, and there's just some race conditions that are a bit hard to address, and I don't think it will be a whole lot of code, but we have to figure out how to do that. That might have to require like doing some LW lock infrastructure work to be able to do that. One annoying corner case on the SMGR or MD.C level is that the sync request queue that we have to wait to make sure that we sync all relations for a checkpoint or at the end of a checkpoint at the moment can't quite be done in a critical section. It almost always works, but if you add assertions to make sure that that's the case, they will fail, because we normally hand off that work to the checkpointer. It's just putting some bytes into a shared memory queue, but if that shared memory queue is full and we can't make progress, then the backend will try to do that that sync at that point itself, and that can fail because for various reasons. Not all of those failures are actually detected because fd.c does a malloc instead of a palloc, and malloc does not have the infrastructure to fail if it's called in a critical section. But like obviously we should not rely on that. Another thing we should do, and this was hinted at earlier with the Btrfs failures with direct I/O, is that we should not modify pages while they're undergoing I/O. That the main motivation for that is not to make Btrfs happy. The main motivation for that is that otherwise we have to copy pages into some sort of bounce buffer before issuing them, and that turns out to be a performance bottleneck. And also an issue for memory management, because we now have to have pre-reserve bounce buffers and shared memory at startup. And the amount of memory that takes on a small cluster is actually fairly sizable. And I found it really hard to find heuristics that had enough bounce buffers without like suddenly doubling the shared memory usage of a Postgres instance with the default settings. And maybe that would have been fine, but it just feels wrong. But also it halves the throughput in some cases to have to do that copy, and that seemed not great. After that, there's a lot of annoying hard work to make actually the logic and bulk strategies that we use to maintain, like limit the impact on the buffer pool of vacuum and stuff, things like that, smaller. They currently have very weird effects on like which buffers are being written out when, and at the moment, they basically are the reason that you can't enable direct I/O, because all that I/O happens basically synchronously from the user space point of view, and if those are blocking, suddenly you get lots of tiny writes and lots of flushes of the wall, and that performs absolutely terrible. So we have to do some smarter logic for like writing out ahead of time, particularly with strategies. There's also a lot of optimizations we can do, like the I/O methods, like particularly worker, but also I/O-ing, were done as simple as possible. And like right now, the number of I/O workers is a GUC that is hard configured. Like you could change it at runtime, but like by doing a SIG-hub, but does not automatically go up and down, and that is not very user-friendly. It would be much nicer if the number of I/O workers increased whenever there's a lot of I/O, and otherwise slowly went down again. And I think there are patches for that already. And with I/O Uring, there's also a number of optimizations that we can make that make it considerably faster, but just add a bit more code. We might also want to add other I/O methods. Like there have been a bunch of talk about using either IOCP or Windows has an I/O Uring clone, I would say. We could use that. I don't really know what the trade-offs there are. We could use PostgreSQL AIO in some limited fashion. The PostgreSQL AIO on FreeBSD has some extensions to the standard that make it less painful to use and faster, so that might be something to do so we can use native AIO in more platforms. And then once some of those were addressed, we can actually start to use AIO for writes, particularly in checkpoint and background writer, but also in backends eventually. And then also one thing that is really crucial to be able to enable direct AIO without like regressing terribly is to be able to do read ahead for ordered index scans. Because right now, if you do an ordered index scan with direct AIO, it will read those blocks one by one by one. And that obviously performs terribly. Today, it only works reasonably well if you have a very good correlation between the position in the table and in the index, but that's not that uncommon. But the performance gains we can get from that are also very large, because if it's not correlated today, the performance today is atrociously bad. And it's also atrociously bad on some operating systems that are less aggressive about read ahead in the kernel. Yeah, I really have to thank a lot of people to be able to get even where we are today, like having some AIO. Without any of those people, I think it would not have worked. And there are lots of other people that helped. Yeah, and I think it's also worth calling out that my employer allowed me to work on the product of this size for 5 years, 6 years. That is not really something to get very easily, to get the employer to invest that much of time with a very unclear payoff or success. So I think that is worth mentioning. Any questions in the few minutes we have?
So we do have time for questions. If anyone has a question, I'll bring the mic to you. All the way back there.
It's not a question, but it's a comment. I was just going to mention that I think one of the things you didn't discuss that was important was that for some of the ReadStream users, there was like years of refactoring that went into actually being able to make the code async friendly. So I too wasted years of my life. And so I think like that's something that will come up as we try to do other big architectural projects is like, oh, you forget you don't just pop in the new code. Even if you make a nice interface that lets you just make one API call, like all of the code might have to actually be restructured. We had to push things down into the heap layer and things like that. So, and you need people to do that, and that it has to be up to the Postgres standard and everything. So, yeah.
Thank you. Do we have any questions?
You mentioned with the worker backend that it could still do better than pushing async into the kernel. I just missed that point, or maybe I misunderstood it. But you mentioned
we could make just the worker logic better too. Right now, we fall back to doing I/O in the backend synchronously if the queue is full. But actually, we do that for the end of the queue. And if you did that for the one that's at the start, the first I/O, it would actually be much better, because now that has the lowest latency, and the ones that are later in the order, like the latency does not matter as much and stuff like that. But I hope I didn't say anything about pushing worker stuff into the kernel further, because I don't know what that means.
Yeah. Okay. Thank you.
Still have enough time for one more question?
At this point, is any of this changing our calculations for how much Postgres page cache we have versus, Linux cache? Just, in other words, is the AIO here also doing direct I/O, or is it still actually able to pull things out of the Linux kernel cache?
It's currently the default will be out of the page cache, and there's an option to use direct I/O, but outside of very, very narrow cases, you should not enable that. And it's the name is debug IO direct.
Okay.
And
so it sounds like it doesn't change that calculation of how big you make your Postgres page cache compared to now.
The 25% is still the wrongest value you can set it to.
Okay.
But leaving that aside, yes, otherwise it should not change it very much. I guess you can benefit a bit more by having a larger buffer pool, but I think that's actually already in 17 a bit more beneficial than before.
I think we're out of time now, so if we give a big round of applause. Please give feedback for our speakers. There's the QR code here and on the doors. It's really helpful for both the speakers and the conference.